Have you ever looked up at the night sky, at that vast sea of stars, and wondered if we are alone? Is there another planet out there, just like ours, a true Earth 2.0? This isn't just a question for science fiction anymore. It's one of the biggest questions driving modern astronomy. Welcome to the incredible hunt for exoplanets. For most of human history, we only knew about the planets in our own solar system. But in 1995, everything changed. Astronomers confirmed the discovery of the first planet orbiting a sun-like star outside our solar system. This planet, called 51 Pegasi b, was a hot Jupiter, a gas giant orbiting incredibly close to its star. It wasn't anything like Earth, but it opened the floodgates. It proved that planets around other stars, or exoplanets, were not just a theory, they were real and detectable. Since then, our catalogue of exoplanets has exploded. Thanks to revolutionary missions like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS, we've discovered thousands upon thousands of these distant worlds. So, how exactly do we find them? It's like trying to spot a firefly next to a giant searchlight from miles away. One of the most successful methods is the transit method. Imagine watching a star from very far away. If a planet passes directly in front of that star from our point of view, it will block a tiny fraction of the starlight, causing a slight, temporary dip in the star's brightness. It's a minuscule change, often less than 1%, but our powerful telescopes can detect it. By observing these dips regularly, we can confirm the presence of a planet, calculate its size, and even determine how long it takes to orbit its star. Kepler used this method to find the majority of the exoplanets we know today. Another clever technique is the radial velocity method, also known as the wobble method. A planet doesn't just orbit its star, the star also moves a little bit in response to the planet's gravitational pull. It's like two dance partners swinging each other around. The star, being much more massive, only wobbles slightly. We can detect this wobble by observing the starlight. As the star moves toward us, its light shifts slightly to the blue end of the spectrum, and as it moves away, it shifts to the red. This is called the Doppler effect. By measuring these tiny shifts, we can infer the presence of an unseen planet and even estimate its mass. This was the method used to find that first exoplanet, 51 Pegasi b. These methods have revealed an amazing diversity of worlds. We found super-Earths, which are rocky planets larger than our own. We found mini-Neptunes, which are smaller gas planets. There are bizarre planets that orbit two stars, like Tatooine from Star Wars, and rogue planets that drift through space without a star to call their own. Some planets are so close to their star that their surfaces are molten rock, while others are frozen ice worlds far from their stellar parent. The variety is simply mind-boggling and shows that our solar system might not be as typical as we once thought. But the ultimate prize in this cosmic treasure hunt is finding an Earth 2.0 foot, a planet that is not just rocky and Earth-sized, but also orbits within its star's habitable zone. This is often called the Goldilocks zone. It's the region around a star where the temperature is just right, not too hot, not too cold, for liquid water to exist on a planet's surface. And as far as we know, liquid water is a key ingredient for life as we know it. Finding a planet in the habitable zone is a huge step, but it's not the final one. A true Earth 2.0 would need more than just the right address. It needs the right atmosphere. The atmosphere protects a planet from harmful radiation, regulates its temperature, and could contain the chemical fingerprints of life itself. This is where the next generation of telescopes, like the James Webb Space Telescope, comes in. The James Webb Telescope is a game changer. It's designed to study the light that passes through an exoplanet's atmosphere during a transit. As the starlight filters through the atmosphere, different gases absorb specific wavelengths of light. By analyzing this light, we can identify what the atmosphere is made of. Are there signs of water vapor, methane, oxygen? Finding a combination of these gases, especially oxygen, could be a powerful biosignature, a potential sign of biological activity. Imagine pointing a telescope at a tiny dot of light from a distant star system and being able to say, that planet has clouds, it has oceans, and it has oxygen in its air. We are on the cusp of being able to do just that. We've already found some exciting candidates. Take the TRAPPIST-1 system, for example. It's a system about 40 light-years away with not one, but 7 Earth-sized planets orbiting a small, cool star. At least 3 of these planets are in the habitable zone. They are prime targets for the James Webb Telescope to study their atmospheres. Another promising world is Proxima Centauri b, the closest exoplanet to us, orbiting our nearest stellar neighbor. While its star is known for powerful flares that might make life difficult, its proximity makes it a fascinating subject for future study. The Kepler mission also found Kepler 186f, one of the first Earth-sized planets discovered in the habitable zone of another star. Each discovery brings us closer and gives us new clues. The search for Earth 2.0 is more than just an astronomical quest. It's a profound exploration of our own place in the universe. It forces us to ask deep questions. What is life? How does it start? And is the recipe that created life on Earth a cosmic fluke or a common occurrence? Every new exoplanet discovered adds another piece to this grand puzzle. We've learned that small, rocky planets are common. We've learned that the ingredients for planets are everywhere. The odds seem to be in our favor. But there are still many challenges. Many of the most promising stars are red dwarfs. They are smaller and cooler than our Sun, which means their habitable zones are much closer to the star. A planet orbiting that close could become tidally locked, with one side always facing the star in perpetual daylight and the other in endless night. This could create extreme temperature differences that might be hostile to life. Also, as we mentioned with Proxima b, many red dwarfs are very active, blasting their planets with intense stellar flares and radiation. So, the road ahead is long. It will require more powerful telescopes, new detection techniques, and perhaps even missions that can one day travel to these nearby star systems. But the journey has truly begun. We are the first generation in history to know for a fact that our Sun is not the only star with a family of planets. We are living in the golden age of exoplanet exploration. For now, Earth is our only home, a precious and unique world that we must protect. But as we continue to scan the cosmos, we are not just looking for another planet. We are looking for a reflection of ourselves, for a connection to the greater universe. The search for Earth 2.0 is a search for understanding our own origins and our destiny among the stars. It's a reminder that we are part of something vast, mysterious, and incredibly exciting. The next time you gaze at the stars, remember that each one could be a sun with its own system of worlds. And on one of them, just maybe, something is looking back. The discovery might not come tomorrow, or even in our lifetime, but the hunt is on, and the universe is waiting to be explored. Thanks for joining us on this journey through the cosmos. If you enjoyed this video and want to learn more about the wonders of space, be sure to hit that subscribe button and ring the notification bell so you never miss an update. What do you think we'll find out there? Let me know in the comments below. Until next time, keep looking up.